לפני שאני אתחיל, יש לי שאלה. מה האפקט של ארוחת צהריים על הסיכוי שתקשיבו לי? אני קורא לזה אפקט השניצל, זה משהו שאני פיתחתי, וכמובן שהאפקט הוא כנראה שלילי, אבל כדי באמת למדוד את האפקט הזה, אנחנו צריכים לעשות ניסוי, להטיל מטבע, חלק יאכלו ארוחת צהריים, חלק לא יאכלו ארוחת צהריים, ואז נוכל לדעת מה האפקט. כמובן שזה לא כל כך הוגן לאלה שלא יאכלו, ולכן בעצם השאלה היא, האם אנחנו יכולים להשתמש בדאטה שיש לנו, על האנשים שאכלו ולא אכלו, שהם לאו דווקא מתפלגים בצורה אחידה, על האפקט של ארוחת צהריים. זה בעצם הלב של השיחה, סיימנו, אתם יכולים ללכת. אז כן, יש לי שקף על זה. אז בעצם, מה שלושת השאלות שמעניינות חברות? חברה רוצה לדעת מה קרה, זה די קל, טבלו, או כל Descriptive Analytics על הדאטה שלך. חברה רוצה לדעת מה יקרה, מה יהיו המחירות חודש הבא, וזה מה שנקרא Predictive Analytics, דאטה רובוט וכן הלאה. והשאלה השלישית, שהיא בעצם הכי חשובה אולי, לפחות לפי דעתי, ואני biased, זה מה לעשות כדי שהמחירות שלי חודש הבא יעלו. וזה מה שנקרא Prescriptive Analytics, כלומר מה אני צריך לעשות כדי למקסם משהו שאכפת לי ממנו. ו-Supervised Learning לא מתאים לשאלה הזאת. מה שמתאים לשאלה הזאת זה Reinforcement Learning ו-Causal Inference, אני לא אדבר על Reinforcement Learning, אבל אני כן אדבר על Causal Inference, אבל מבחינתי זה שני תחומים שהם מאוד דומים. אני מדבר בעברית וחשבתי שאני אמור לדבר באנגלית. Anyone don't speak Hebrew here? Okay, so I'll switch to English. The slides are in English, so anyway, you can follow. So the summary of the talk is you have data, you use causal inference magic, and you make better decision. Sounds like something important in life, right? And recently, two researchers got the Nobel Prize exactly on this field, on how to infer causality from data. I really recommend you to read the paper in the Nobel Prize website where they describe both in layman language and both in scientific language why did they got this prize. And these are the methods we use in Vianai as well. Before, like usually people put this slide in the end, but I always forget, so I'm being rude and I'm saying that like why I'm really here is to recruit people, DevOps and backend engineers, and secondly, we look for design partners. If you have problems that you would like to solve, which are related to your periphery of your business, like if it's the AI with the center of your business, this is not where we aim to help. We aim to help in the periphery, marketing, sales, customer relationship, product optimization, and stuff like that. So now that I finished with this promotion slide, I can go back to the content. And why making better decision is valuable. So here you can see a report by McKinsey & Company about the value unlocked in trillions of dollars for AI. And the largest fields are marketing and sales and supply chain management. So if you are thinking about building a startup, concentrate on these two fields because the most of the money is here, but most of the competition is here as well. And these two fields, actually any field, is about making this better decision. In marketing, you want to make better decision about which campaigns to put more budget on and so on. In supply chain management, you would like to know how much to manufacture and what to manufacture and so on and so forth. So it's all about actions and effect of the action. Like eating lunch and the effect of you listening to me right now. So industry experts say that in the future, causal inference will become much more dominant for helping business to make decision. And you can read the blog about this in the Causal Science organization. But it's not only the future. Large companies already today use causal inference and they claim that causal inference actually really helps them to improve their businesses. You can look at Uber, Netflix, LinkedIn, Google, Microsoft, all the tier 0 technological companies use already causal inference. Just today, Amazon published that apparently these two Nobel laureates are affiliated to Amazon, and Amazon uses their methodology a lot to improve their business. So we see that proof that causal inference is important. And the slide, there is no effect of pressing the remote control on slides. Why not just prediction? This is the most common question I've been asked by data scientists. Why the hell do you need causal inference? Just predict and that's it. So I'll give you an example, illustrative example. One of the most common tasks or projects that I've ever encountered in my career as data scientist is predict churn. Who predicted churn in his life? Yeah, you can see it's very common. And the thing is that it's wrong to predict churn. Why is it wrong to predict churn? Because usually the framing is like this. Tell me who are likely to churn and then treat him, like give a discount or whatever. Why is this wrong? Because you can actually think about 4 types of population. There are people that will not churn anyway, people who will churn anyway, people that if you target them, like you send them an email, they say, I hate this company, I will unsubscribe, and they churn. And last, there are people that will actually, you'll benefit from targeting them. These are the persuadables. And these are not necessarily the people who are most likely to churn. These are the people who are most likely to change their behavior, are most likely to be affected positively by the treatment. Is this clear? Understanding the difference between the previous slide and this slide, worth 300% better churn prevention. This can be read in a paper in the Marketing Research Journal, which is like the top journal in marketing. They compared between the 2 approaches and showed that it's worth 3 times better result when you measure just how much churn did you prevent. So let me give you an example. One of the most popular usage of causal inference is what's called uplift modeling. Uplift modeling is related to who should I target and with what. Now imagine that we could have known what is the effect per user. Like we could have told you if the user will be positively affected or negatively affected. And now we sort people according to their effect in a descending order. So first we put people who are likely to be positively affected, and then we put people who are the least, will have the least effect or even a negative effect. And now when we sort people according to the effect, if we look at the cumulative effect, like how much sales do we get or so on, it will grow because we target the people who will actually benefit from the effect. And then it will not change because we target people that will not change their mind in any way. They are lost causes, they will churn anyway, or they are sure thing, they will not churn anyway. And last but not least, we will target people that actually targeting them have a negative effect. Is this graph clear? Okay, great. So what does A/B testing do? A/B testing actually checks whether treating all or treating none, which one is better. And you can see treating all is better than treating none. But causal inference, or uplift modeling specifically, can tell you that actually targeting only part of the people will have better performance than targeting all. So causal inference can be used even when you are experimenting for studying the heterogeneity in your data. So targeting none or targeting all is not the best thing. The best thing is what's written here with a very complex equation, which says if the effect is positive, target. If the effect is not positive, don't target. Very simple. Now, does this work in real life? So with one of our design partners, we had a project where they wanted to know whether to target people or not, and there was no experiment. We just took natural data. Some people were more likely to be treated, some were less likely to be treated. And we created this exact plot using the observational data, no experiment. Now we wanted to validate whether our policy is the transformation from data to action. This is actually what we are trying to do. We're trying to learn a better policy. We experimentally showed that there was an uplift of 30%. So, and again, this is without experimentation for learning the model, experimentation only for validating the model. And this is a good place to say that we are looking for more design partners to prove our approach and to help us develop our platform, talking with the end users. How can you make better decisions? So there are 3 resources to make better decision, maybe 4th. One is to pray that God will tell you the best approach. But if you are secular, you have only 3 approaches. Either you do a control experiment. This is what scientists do, right? If you want to know what is the effect of gamma radiation on flowers, there is a book like that, then you will need to do experiment, and then you know what is the effect. Easy, but sometimes expensive or impossible. For example, if Uber wants to know what is the effect of changing the price per drive, they are not eligible to, like legally, to give different prices to different people. Let's imagine that this is like that. Or for the drivers, they cannot tell one driver you will earn more than another driver. So sometimes experimentation is impossible, like who will eat lunch in a conference, or it's expensive. So I'll strike this because it's not always possible. But as I just showed you before, even if you do a control experiment, you can still use causal inference to get a better approach, a better policy than just doing A or B. Then you can do simulation, deep mind stuff. You can play Go or chess or everything that you can simulate easily, even poker. You can find reinforcement learning is like the way to go to find the best policy. But you not always have simulation. Like if you think about customer relationship, it's hard to simulate a user. So although reinforcement learning is my beloved son, this is like the field I love most in machine learning, the one that is actually applicable when you have observational data is mainly causal inference. Now, causal inference and reinforcement learning are actually the same thing. It's like two communities, two churches, if you will, but they are talking about the same things. They're talking about outcomes and talking about actions, and recently there were a few papers talking about how to merge these two approaches. What is the fundamental problem in causal inference? The fundamental problem is Gwyneth Paltrow. She doesn't know it, but she's the fundamental problem of causal inference. Why is that? Think about the movie Sliding Doors. Who've seen it? It's a really bad movie, so the people who have not seen it, I don't recommend. And the effect will be negative for your life. In this movie, the actress, once she gets into the, not the actress, the character, once get into the train and once she doesn't. So you can think about this as the treatment. And then you can look at the outcome, her life. In one, her life is shitty, and the other one, his life is even shittier, okay? But in reality, you cannot know what would have happened if you hadn't tried what you actually did. Well, this was a complex sentence in English. Most likely I made the tense not correctly, so I will just show it with numbers. Sometimes you have the treatment, you do the treatment, sometimes you don't do the treatment, and you have a bunch of outcomes. Now imagine, and this was like a breakthrough paper, although it's like kind of obvious, you can imagine potential outcomes. What is potential outcome? What would have happened if I did something else? So when you don't treat, you know what would have happened if you don't treat. But you don't know what would have happened if you treated. And when you treated, you know what would have happened if you treated, but you don't know what would happen if you don't treat. And what we actually care about is the effect. What is the difference between the outcome when we treat and the outcome when we don't treat? So you can see all these question marks where we have like half of the data, and when we actually want to infer the causal effect, we don't know anything, okay? So it's like a paradox. How can we actually do causal inference if we don't know anything? So I will show you in the next chapter when is that possible and how. Causal inference is also important because of misleading attribution. For example, eBay published a paper in 2015, and recently Twitter too, I think, that for each dollar they spent, they earned $4. So they're happy. Wow, we make a lot of money. We have 400% return on added spend. But actually, they turned their advertisement off because they were negotiating with Microsoft. They tried to get a better price, so they said, we don't publish anymore. We stopped the advertisement. And they saw that actually there was almost no effect on their sales, meaning they are losing money. They thought they're earning money, but they're losing money. And this is because they didn't take a causal approach. They didn't think about the effect of advertisement instead of this false attribution, meaning some of the organic traffic was attributed to the paid advertisement. So, and another problem when causality does not take into account, where like I'm learning causality for the last 2 years, and every time I learn more about it, I say like, wow, I was so stupid before. And it's a huge field, and I discovered many mistakes I did in my 20 years career as a data scientist, that if I would know this field, I would have done it otherwise. For example, spurious correlation, it's very well known, but it can be shown very easily for a business analyst. Think of a business analyst is asked whether exercising reduces or increases cholesterol level. So he plots the scatter plot and he says, the more I exercise, think about it in a business term, I don't know, the more I spend on the ads, the better is my revenue. So this is a good ad. I pay more, I get more leads. But we know scientifically that actually exercise reduces cholesterol. So how can this be? How can it be that we see positive correlation, but actually the causality is opposite? Any answer, idea from the crowd? Okay, what's the name of this paradox? Serum-Son paradox, right. There is some intervenient variable, for example, age or something. You can imagine anything. That for older people, they tend to have higher cholesterol levels, and they also tend to exercise more. So if you stratify, meaning control for this confounder variable in causality terms, then you will see the real effect. So this is like a toy example of how naive analysis could be misleading compared to a causal analysis. So until now, I just told you that causal inference is important. All the big companies do it. People discovered that they waste hundreds of millions of dollars because they don't do it right, like eBay and other companies. But it's very neglected in the data science community. Like this is a survey from Kaggle 2020, where they ask people what kind of method do they use in their common life. You can see linear logistic regression. Like there is this joke that for investor it's AI, for the company it's machine learning, and in the end it's logistic regression. And causal inference is maybe here. 4.5% of the population, maybe or maybe not. Like the upper bound is 4.5%, but I guess other means many other things. So it's very, very non-common to use causal inference, although it's very important. Very important. So how do you do causal inference? So actually there is a huge course online, which is free. The causal inference course by Brady. He used to be a Ph.D. student until recently. Now he has his own company about causal inference. So he has a course on causal inference, and I'm talking with Kostya. Where is Kostya? Maybe to give some kind of, how do you call it? Community course about causal inference. So it's very hard to summarize everything, so I just summarized the main concept. So the main concept is that there is something called the causal DAG. DAG stands for directed acyclic graph. There is something true in the nature where something affects something, okay? Exercise affects cholesterol levels. And it's important to know that because otherwise you could do the estimation wrongly. But not always it is known. You can interview a domain expert or something to know this. But if you don't know it, there are methods called causal discovery, which will try to estimate, like there is a theory that you cannot actually estimate it, because for the same different causal relationship, the data will look the same. But there are some approximation methods that that enable you to guess the causal direction. Actually, there was a Kaggle competition about that recently. And in there is a Bosch paper which talks about how they were in a factory were able to find the variable that affects their yield. So you can do that, and then you can think about this potential outcome concept that I told you, which is like imagining what would have happened if you did something else. And why do you need these? Because you want to estimate this because you want to measure the average treatment effect. Like what is the effect of eating lunch minus the effect of not eating lunch for how well do you listen to my lecture right now. But you also care about Kate or individual treatment effect or treatment heterogeneous effect. It's like different names for the same thing, which is measuring the effect per person. Maybe female are affected by lunch differently than male, or maybe old people are affected by lunch more than young people and so on. So you also affect about how does this change with a function of x, and x being the characteristic of the unit that got the treatment. And the two most important things, which sometimes data scientists miss, is policy evaluation and policy optimization. Policy evaluation is, okay, I imagine some policy, I don't know. I give lunch to young people, but I don't give lunch to old people because they will fall asleep. So, and then you say, okay, given this policy that I invented, what will be the performance of the lecture? But this is not enough, because we want to find the optimal policy, not necessarily the policy that we came up from nothing. And this is this thing. It's like finding the best policies, again, is the transformation between observable variables to the action. So we would like to find this optimal policy or optimal way to take actions given the data. And this is like the holy grail. If you manage to do better, then you earn money. That's why the title of the talk is Causal Inference for Business Outcomes. What is the difference between supervised and causal learning? We already talked about it a little bit, but in supervised learning, you care about the outcome. In causal inference, you care about the effect. In supervised learning, you actually assume that you are a passive observer. You predict the weather, but you don't affect the weather. Where in causal inference, you are a decision maker. You are proactively change stuff. And that's why in supervised learning, you usually assume that the train and test data distributed the same, but in causal inference, you are making action. So by definition, you will change the distribution, right? If I do something, I will change how the world look like. Validation in supervised learning is pretty easy. You use cross-validation, holdout, whatever. But in causal inference, it's actually one of the fundamental problems. There are papers still published about how can I know whether one model, causal model, is better than the others. There were some breakthrough by Hasty, the one that wrote Element of Statistical Learning. He's like one of the most famous data scientists, the researchers in the world. So he published some paper about how can you cross-validate a causal model. Feature set. So in supervised learning, we know usually that we can add a feature, we can take out a feature. Usually it's like a quantitative difference. Maybe performance is a little bit better. In causal inference is the terminal. Like if we take some variable that we shouldn't add it to the model and we add it, we can ruin the model. We will get bias. And vice versa. If we don't put some variable that we should have put it, then it also can cause our model to be completely wrong. This is why understanding the causal relationship in the data could be very helpful to make the right modeling. And this is related to the last point of domain knowledge. Like in deep learning revolution, we've seen that all these handcrafted features for images worth nothing, because if you just throw everything to the deep learning, everything works by charm and you don't need domain expert. But in causal inference, they are useful. It's very useful to interview the domain expert to understand that you are not doing something really bad. Okay, I'm a little bit out of time, so I'll talk just about the typical phases in a causal project. You define the model, you identify, meaning how can I turn the causal question into a statistical question. Then you estimate the effect, then you evaluate and optimize your policy, and last but not least, which is the most important, you refute, meaning you validate that the result is real and not some mistake in your assumptions. I will skip a little bit about the math. One of the most important assumptions that should take when you do causal inference is positivity, meaning you should take data only when a treatment is either is sometimes given to some people, maybe, meaning if you always send the discount, I would never know what would happen if you didn't send a discount. And if you never send any discount, I will never know what would have happened if you did send a discount. So the data that you need in order to do causal inference is something where the probability for each treatment is larger than 0. And actually we just published, except our paper was just accepted to Causal Data Science Meeting 2021, where we talked about how to detect whether the data is actually positive, has positivity violation or not, meaning whether we have some situation where we always treat or always don't treat, which could harm the analysis. Okay, so how do you estimate causal effects? One of the simplest way is just to do stratification, meaning we cut the data to pieces, and for given an X, given, I don't know, the gender or the age, we estimate the effect, and then we average according to the probability of X. And this is a short proof that you can look after the class, after the talk, to see why this is true. Another way to estimate is something called matching. Matching is to make the non-RCT data as if it was RCT by finding identical twins. So if this is someone who was treated and he was fat, I find another fat person that was not treated. And if this person is thin, I'm trying to find another thin person who was not treated. And if I do this again and again, I can actually create a data set which looks like RCT, although the real data is not a randomized controlled trial. I create a data which is as if randomized controlled trial. This is a classical method that most like in modern analysis, it's not been used, but it's important to talk about it. Another way to do this matching, this is a matching in high dimension. Like imagine X is like 100 features, so I need to find the nearest neighbors or something in a large dimension, which is problematic because distance has no meaning in large dimension. If you don't understand this, you should go to the supervised learning course I teach. And so instead you can do something called propensity matching. It can be proved that if you match units or people by the probability to get the treatment, it's almost the same as matching and even better. This is explaining the propensity is just the probability to get the treatment. Last but not least, there is something called IPTW, which is inverse propensity treatment weighting. And the concept is like this. Imagine people are red or blue. You can think about it as male or female. And red people have tendency to get treated. And blue people have the tendency to not get treated. They are usually in control. Now, if you will measure the effect of treatment, it's biased because when t equals 1, you mainly take red people. But when t equals 0, you mainly take blue people. So if you just compute the expectation of t equals 1 minus t equals 0, you will get a biased result. So how do you fix this? You give a larger weight to the things which are less probable. So for t equal 1, you multiply this by 3, by 4, because 1 over 25% is 4. So you take 4 blue people. And for the red people, you also take 4 red people. So you just multiply your samples by the inverse probability to get a balanced population. How do you do causal inference in practice? This is like the most important. There are many packages by top leading companies like Microsoft and Uber. Booking.com has also published a causal inference package recently, specifically on uplift modeling in large scale. And there is the list of the open source I know. EconML was not here, so I added it. So to summarize, causal inference is hard because it's the entrance barrier is high. You need to learn a causal inference course and to practice because there are many pitfalls, not like in supervised learning. And this is mainly because it's hard to validate and evaluate. You don't have a holdout set in which you can measure your performance and see whether you did it correctly or not. And sometimes domain knowledge is needed. It's not always needed, but many times it is needed. Like if you have a time index, maybe it's easier because you know that something from the future cannot affect something from the past. This is something we use extensively. But it's very valuable. You can optimize decision making, or what's called incrementality. You can improve KPIs. You can go to a business owner and say, I can improve your retention. I can improve your lifetime value by making better decisions. And you can detect real effect and get rid of false attribution. You can think that something is very valuable for you, but actually it's not. And you can do personalization. This is what I showed you with the graph that looks like a hill, where you can measure what is the effect per person and do personalization. I have a gift for you, which is a code, which based on no package. I just wrote everything from scratch in Python, so you can look at after it in your free time and see how causal inference can be done just with pure Python. It's a toy example, so don't get too excited. And if you want to reach me out, you can email Hanan and Vianai. And I have not published official office hours because I didn't know it exists. So you can just contact me just after the talk, and I will be there for half an hour waiting for you. So come in your masses. Thank you very much, and I hope you get causal inference is important and interesting.